As I mentioned at the opening of the presentation, we are fortunate enough to have Paul Stechik presenting to us today on harmonic filter design. Paul is the president and co-founder of the Northeast Power Systems Inc., or NEPSI, as it's abbreviated, which is the leading global supplier of medium voltage metal enclosed power capacitor banks and harmonic filter systems. Paul has provided engineering and product support to owners and operators of small and large industrial, commercial, renewable and utility power systems through NEPSI for over 25 years. Paul has also published over 30 technical papers and is an expert in harmonic analysis, filter design and application, as well as power systems analysis and manufacturing design. Paul has previous experience as a power systems engineer at Power Technologies Inc., located in Schenectady, New York, where he was responsible for various power system studies, including system-wide voltage sag studies, harmonic analysis, and filter design studies, as well as load flows, short circuit, protective coordination, and transient analysis studies. He's also worked as an application design engineer at Commonwealth Sprague Capacitor, or CSDI, located in North Adams, Massachusetts, designing, developing, and building low voltage automatic power factor correction equipment and harmonic filters. Paul holds a Bachelor of Science and Masters of Engineering degrees in electrical power engineering from the research of Rensselaer Polytechnic Institute in Troy, New York. And with that introduction, Paul, as I said, really looking forward to hearing more from you and seeing your presentation. I will hand it over to you so you can start the formality.
Okay, great. Thank you, Matthew. Thank you for the introduction. And I will share my screen. Okay, share. Okay, guys, you should all be seeing my screen. And once again, Matthew, thank you. I am with Northeast Power Systems Inc., NEPSI. And for those who are looking to contact me, I'm on the lower left of the screen here, paul.stechik@nepsi.com. And we do have some local representation. He's a direct factory contact. His name is john.wright-smith@amsc.com. We are part of American Superconductor, who's a producer of STATCOM systems, which is a different version of reactive compensation. So today's presentation, we'll be talking about harmonic filter design. I do have the chat box open here, and my plan is I'll try to monitor the chat box. If you have questions as you go along, if it makes sense, I will answer those questions right away. We do have quite a bit of material to cover. I actually might not get through all of the material, but let's see what we can do. So just to give you a feel for, well, what's a harmonic filter look like? Well, here's a very large harmonic filter system. This is what I've been doing for the last 25 years. Since getting out of college in 1990, I've been involved with harmonic filter design for a good 25 or 30 years. We started this company called NEPSI, which manufactures these reactive compensation solutions, these harmonic filter systems. So I have over 25 years experience in developing these systems. This is a very large system that you see here. It's a total of 54 megabars, 2 harmonic filters here. And the question that everybody always asks when they see these pictures is, what are those things on top? Those things on top are resistors. And we'll be talking about those today. They're harmonic filter high pass resistors. And they change the shape of the impedance curve of harmonic filters. So we'll be talking about those resistors on top. But when you look inside this enclosure, what you see is a complete harmonic filter system consisting of multiple stages. And in this case, oftentimes we reference filters with an F number or a filter tuning point. And in this case, it's a 3rd branch, a 5th branch, a 7th branch, 11th branch, and 23rd branch. This enclosure system you see here contains all switching protection controls, a complete harmonic filter system. So today we're going to be getting into, well, how do we fit these components, and a little bit about basic filter design. and maybe perhaps I might touch a little bit upon how the harmonic filter system is controlled and protected. I have a couple of slides there also. But the primary purpose of today's presentation is to talk about the LRC parameters. When you look at this filter design, what you see are various tuning points, and you see various types of filters, C high pass, notch, and high pass type filters. We'll be talking about those three. Harmonic filters, what are they and what do they do? And this is a key point that I often like to cover first. Harmonic filters in general are installed for three primary reasons. The first one is to correct power factor. And this is something that some people may not understand is most oftentimes a harmonic filter is being installed to correct power factor. That's the dominant reason why the harmonic filter is being installed to correct power factor. Harmonic filters provide reactive compensation. They have a VAR output. To the right here, I show a notch harmonic filter. It consists of just the reactor and a capacitor. The purpose of that reactor is to tune this capacitor to a harmonic. Okay. Typically, the reactance, the XAL of that reactor, it is 1 over the tuning point squared of the capacitive reactance down here. So when you think about a filter, it is primarily capacitive at its fundamental frequency, 50 hertz or 60 hertz. So think of a capacitor bank, think of a filter bank as a capacitor bank. The next reason it is installed oftentimes is to prevent harmonic resonance. I kind of have these out of order, unfortunately, but oftentimes harmonic filters are put in because you have to do power factor correction, but you want to prevent resonance. So a customer comes to us, they need reactive compensation, they're trying to avoid a power factor penalty, and they look to install power factor correction. They do a resonance analysis, they do a harmonic analysis, and that harmonic analysis determines that yeah, I got a resonance issue. Well, you put the filter in to prevent resonance. The second reason why most filters are installed. And then finally, the third reason is that you need to filter the harmonics. You're trying to meet an IEEE standard or an Australian standard for distortion, or maybe it's a local utility standard. You're trying to meet that standard either for voltage distortion or current distortion, and a filter provides a low impedance path for harmonic current, and also helps to reduce voltage because of that low impedance path. So that's the third reason. I have a large mine system as we show it here. You can see here this is a conveyor system, but mine projects have crushing mills, grinding mills in them. They use cycle converters, large VFD drives, cycle converters sometimes on the order of 25 to 30 megawatts in power consumption, producing a significant amount of nonlinear load. We're chopping up current, we're creating harmonics, and you don't want that harmonic current to flow out into the network. So what do? We put a filter system in to pull that harmonic current from the power system at the mine, so that it doesn't flow out into the network and pollute the network. So that's the purpose of oftentimes of a harmonic filter. So most simply stated, what are they? Well, it's a capacitor bank with a tuning reactor. And so that's what you see here. Very simple, we're putting a tuning reactor in there. So we're gonna be talking about those two plus resistors. It's also important to note that oftentimes harmonic filters come in basically three configurations. One configuration consisting of the metal closed solution. This is what NEPSI does. This is what we developed our country based upon our company. It's a fully integrated solution. The open air solution, the one to the right here, is also a filter, and it consists of air core reactors rather than iron core. So a big difference between metal closed and open air. The primary difference is this air core reactor. Okay, so instead of the inductor, which tunes this capacitor branch, which is sitting behind it, instead of it being an iron core reactor, it's an air core reactor. So we're going to talk a little bit about air core, iron core reactors. And incidentally, this box here to the right, What is it? It's a resistor. So we put the resistors on top of our enclosure when we have resistors associated with our harmonic filter. In this case, you can see that the resistors are put off to the side. So open air, metal closed, they're the two configurations we're talking about. And we'll be touching upon both of those today. Here's another example of a harmonic filter that's air core on the right. Because it's, and here you can see we have 5 stacks of reactors. They're stacked up, 5 of them. You can see the resistor cages here developing the harmonic filter branches. So again, air core reactors. There's also an E-house type solution, and also another very common way of doing harmonic filters, and that is to take an E-house and to put the reactors, capacitors, and resistors into the E-house, put some air conditioning on the side, and you have yourself a harmonic filter also. So another way of doing it. It's not something that's used too widely in North America or South America, but it is certainly used in other parts of the world. And this is how that solution looks on the inside. And incidentally, this E-house solution shows air core reactors, but many E-house solutions use iron core reactors. So we have a question that I'll take a shot at some of these questions as we move along. Dan Martin asked, do you find that the same harmonics are always there so that the filters can be tuned and left, or do the harmonics change throughout the day and thus the filters need to be adjusted? So that's a good question, Dan. What Dan's asking is are the harmonic currents in the network changing throughout the day? If so, do we need to make changes to the filter systems on a day-by-day basis? The reality is some devices, especially cycle converters, for example, their harmonic output does change depending upon the operation of the mill. So harmonics within a network do change from one point of the day to another point of the day. The harmonic filter system, however, does not change. It's a fixed passive solution. If we go back to our original design here, you can see here we have multiple stages. So in this case, we're switching in basically 5 megavar steps, 5,600 kvar steps at different branches, but we have different types of filters and different tuning points. So the long answer to this is the harmonic currents can change, but the harmonic filter system must accommodate those changes. So normally what is done is a harmonic study is conducted, and the harmonic study determines the key operating points of the system, what are the harmonic current inputs to the system at various points in the day, and the harmonic filter must be designed to accommodate all of those conditions. And incidentally, some filters are better at flexibility, being flexible, being able to do different types of harmonic currents, and we're going to be talking about those types of filters today. We'll get to Kenny. We'll get to your question a little bit later. We'll talk about that. So reactive. When you look at key filter ratings, well, okay, the first key filter rating is reactive power, and it's usually based on the requirements of the load. So a load study gets done, somebody develops a spreadsheet, or somebody does a harmonic load flow study. They come up with what is 60 hertz or 50 hertz reactive power requirements of the facility, and that's usually the first parameter that defines a harmonic filter. The first parameter that defines a harmonic filter is its reactive power output rating. And I make that statement, it's an output rating. What is the output rating of the reactive, of the harmonic filter? It's not the amount of kvar installed. Remember that the capacitors inside a filter bank, generally speaking, the harmonic, the kvar outputs from those will be greater than the overall output of the harmonic filter system. So we're using higher voltage, higher kvar rated capacitors inside a harmonic filter. Next key rating is voltage. Obviously, if we have a 33 kV system, the kvar output is based at 33 kV. It's your line-to-line voltage rating. Installation level, the impulse rating, the 1 minute withstand. Okay, that's based upon typically the base voltage of the system, plus elevation concerns, plus pollution concerns. Those types of concerns are also potentially raising the insulation level, the impulse rating, the BIL we call it, and the 1 minute withstand. rating, which is a 60 hertz or 50 hertz application of voltage at the terminals of the filter bank. Tuning point is another key parameter. What are the tuning points of the harmonic filter? Okay, and oftentimes we might say, well, we have a 4.7 tuned harmonic filter that's equal to a 282 hertz tuning point. Okay, so we take 60, in this case, this is based upon a 60 hertz system, 60 times 4.7, I get 282 hertz. So that's where that comes from. There are three main types of harmonic filters being used in major industrial plants, and this includes renewable power plants, also that we're involved with notch, C-high pass, and high pass filters. They are the three types of filters. When you supply a C-high pass filter or a high pass filter, you have what's called a damping factor associated with it. And that's equal to the R over X at the tuning frequency. And I underline that, tuning frequency. So you have to figure out, well, what is the value of X, the inductor that's being used in the filter? What is the value of that value of X at the tuning frequency? So if it was a 4.7, as we've indicated here, I would take 4.7 times 2 times pi times F times L of the inductor to come up with the value of X at that frequency. And then from there, we would calculate the value of R to come up with a damping factor. So damping factor is a very important parameter when defining C-high pass and high pass type filters. So generally speaking, as you lower, okay, the damping factor, as you go to a lower value of damping factor, you're increasing the kW, you're decreasing the ohms, and as a result, you're increasing the cost of the filter. So we're going to be talking about resistor in a few minutes. And then, of course, fundamental current rating. Okay, what is the fundamental current rating of the filter? Well, it's basically the reactive power divided by the square root of 3 divided by the voltage to come up with that. But we want to state what the fundamental current is, assuming a 10% over voltage. Don't forget the utility is going to supply a voltage, and typically it could be plus minus 10%. So all your ratings should be assuming that we have a 10% over voltage rating in the system or an over voltage condition in the system. And then finally, harmonic current ratings. What are the harmonic current ratings? What harmonic currents do we expect to flow into each of these branches? And I make a statement here to be very conservative. I can't overstress the importance of being conservative. When you develop a harmonic filter, if you are not conservative, it will come back and bite you. It's a true fact. Oftentimes we see consulting firms develop a specification. The specification will be based upon the results of a harmonic study, and they will specify those exact harmonic currents that the harmonic study put out. That's just simply not a good practice to follow. We recommend a significant amount of conservatism be put in there into that filter design. Because why? Because systems change. And so we'll talk about that here a little bit. So how are filter ratings determined? Power system studies, number one, load flow studies, or you're doing some type of load study and you're coming up with this reactive power rating. After you come up with a reactive power rating, you develop a harmonic analysis. That might be with Dixielant, I think is what maybe is the primary software used in Australia. But there's other programs like ETAC, Easy Power, SIME, all different types of programs, but you're doing a harmonic analysis. And what is the purpose of harmonic analysis? Is to determine and calculate the voltage and current distortion throughout the entire network, and also to determine the harmonic current flow that will flow into the harmonic filter, so that then you can come up with the filter parameter ratings, L, R, and C. So filter design is an art. It's an art. There is more than one filter design that can correct a system's voltage and current distortion to make it compliant with, say, the local standards for voltage and current distortion. So there's more than one design. Some designs are, of course, better than others, and experience will make you a better designer without a doubt. And then also understanding the cost implications is also very important. and understanding the reliability is also very important. How does my choice of LRC, how does my tuning points affect the reliability of the filter? And these are things that also come with experience. So once you have a harmonic analysis complete, the next step normally is to come up with, well, what capacitors and what reactors and what resistors should I use? Okay, you have to come up with voltage ratings and current ratings and watt ratings and kVAR ratings of these devices. And that's not typically done with a harmonic analysis. It's typically done with a spreadsheet tool. So the filter design is determined by harmonic analysis, the choice of tuning point, the type of filter. But in the end, typically you're using some type of spreadsheet tool to come up with those values. We have this tool available to everybody. It's on the internet. It's under, just follow this link here. Go to nepsi.com and follow the resources and go to spreadsheet tools. We have many spreadsheet tools there, but this is a great spreadsheet tool. We've been using it for many years, and it's been developed and pushed along, and it's been vetted many, many times. And the way I know it's been vetted is because we receive harmonic studies from people with recommendations for component ratings. We punch those values into our spreadsheet, and this is how we confirm the ratings. So just a couple basic concepts for harmonic filter design. What I showed here on the right is a very simple system. I have a source equivalent. This represents the utility power system, what's feeding an industrial facility. I have a point of common coupling. This is a common thing for IEEE 519, is we need to determine what the current distortion here is, and voltage distortion is here. And the filters down at this point must limit the voltage and current up here. And these are the standards that we typically follow in North and oftentimes also in South America. I have a harmonic producing device here, and this harmonic producing device is injecting harmonic current. Harmonic current injected from VFD drives and adjustable speed drives, cycle converters, rectifiers. Remember, those devices are chopping up the current. They create a harmonic current source, which I show over here, and they're injecting harmonic currents. And they're considered an ideal current source, meaning that no matter what my impedance is here, these currents are being injected into this network, okay? The amount of harmonic current that flows into the filter here, the amount of current that flows into the filter here is just based upon an impedance divider between here and here. It's that simple. It boils down to that simplicity. An impedance divider between those 2 points. It's looking at the impedance of the source versus the impedance of the filter. Now, obviously, this is a very simple system because we only have one filter branch. But what I show here is the filter here, the filter impedance here. This is a 4.7 tune filter, and I also show the impedance of the source, that dashed line. That's this impedance here. And the amount of current at each and every harmonic is calculated by looking at the ratio of those impedances. It's an impedance divider. But you must pay attention to the fact that these are polar complex impedance quantities. They have a real component and a complex component. If I go from looking at the 2 impedance values and then instead look at, well, what is the impedance if I look into the circuit from here, I get this magenta curve, the total impedance curve. And obviously, the reason why filters work is that they look to minimize the impedance of this network. We have a source impedance in parallel with another impedance. And of course, along that whole distance here, we have less impedance and therefore less voltage distortion because we're pulling in current here and it's going through less impedance. We've reduced the impedance, except for at this location, which we refer to that as an anti-resonant point, but it's basically a resonant point that exists below the filter tuning point. Whenever you put a filter onto a system, you have a low impedance point or a partially low impedance point, depending upon the type of filter, and you also have a resonant point that you must always be thinking about. Okay, what is the impact of that? So that's basically the basics of harmonic filter, of how harmonic filter works. It offers a low impedance path to harmonics. Okay, so Jason's got some interesting question. He's asked the question, have I witnessed or has NEPSI witnessed any issues when connecting a filter in close proximity to other existing installations with filters already connected, shifting resonant frequencies, impacting performance of existing installations to meet allocated emissions? The answer to that question is yes. We have seen that. Whenever you install filters on a system, you must consider the entire system, the system as a whole. And I don't have a whole lot of time to get to it, but oftentimes you have filters tuned to different frequencies at different locations. When you inject harmonic current into the network and you have the two filter systems side by side, you can enter a situation where you actually have some resonance amplification between the filters. So it's important that whenever you do harmonic analysis, you ask the questions, are there other harmonic filters nearby? They must be modeled. Are there other capacitor banks is even more important. And we have seen failure in capacitor banks because of being put next to a harmonic filter. So yes, very important to consider that. So the most common types of filters are notch, high pass, and C high pass, and as indicated here, the cost goes up as you go up with that type of filter. So generally speaking, we are trying to use notch filters when we can, but if the situation calls for a different type of filter, we'll go to a high pass filter, and then for frequencies below the fifth harmonic, we'll go to sometimes a C high pass filter if we need to do a significant amount of dampening. So key here is we're dealing with a resistor across a inductor capacitor here, a resistor across the inductor here. These two filters are very similar in their impedance characteristics. The key difference there is that this one is missing its fundamental losses. The loss is at 50 hertz or 60 hertz. And that's because this X of L here is tuned to X of C here. And they're equal to each other at the fundamental, meaning no volts here, meaning no volts across the resistor, meaning no losses in the resistor. It allows us to decrease the value of the resistor here to a much lower value, a lower dampening point, which means it's a higher damped filter system. Can't get into it too much. When you look at the characteristics of a notch filter, it's very simple. We come from the impedance at the fundamental, we drop down to a tuning point, in this case around 4.7, and then we shoot up. Very simple. We have a low impedance point where we have set the X of L at a ratio about, in this case, 1/4.7 squared of X of C. And we're going to get into the calculation in a minute. A high pass filter is shown here, and we have a value R parallel with the value X, the inductor. And you can see here at the impedance curves, filter impedance on the y-axis and harmonic current, harmonic number on the x-axis here. So you can see that by changing the value of R here, we can change how the shape of this filter impedance curve looks. Obviously, if we bring R to infinity, to a very high value of ohms, it's like it doesn't exist, and then it looks like a notch filter. And that's what you see here in a blue curve. Okay, Q of 10 almost looks like a notch filter, right? It has a very similar look to a notch filter. So to some degree, you raise the value of R, it becomes a notch filter, which means that the calculations required to calculate X of C and X of L here are basically the same. The only thing that changes is we're adding a value of resistance, which determines the the shape of the impedance curve. But the tuning point is always calculated the same, whether it's a high pass, C high pass, or a high pass filter. The other thing to note here is as we go up in frequency, we offer lower impedance to the system. We offer lower impedance. So these filters, as you can see, they're high pass filters because they're passing high frequency currents into the filter. It's offering a path around the reactor through the capacitor. The high frequency, if you think about it, X of L is going to be high, X of C is going to be low, and the value of R is going to be constant with frequency. Technically it's not, but let's just say for simplicity it is. Current will want to flow through the resistor because X of L got very large, so we get this characteristic shape that you see here. A C high pass filter, incidentally, has the same exact characteristics of a high pass filter. All we're doing is shifting some of the capacitance from here up to there, a portion of it, and we're putting it inside the resistor leg here and here, so that we can tune this inner branch to the fundamental frequency of the system to reduce the losses in the resistor. And this becomes desirable in systems where we need to provide a lot of dampening. Okay, so higher dampening, and we get lower losses. So you pay less for the resistor because I got lower losses. I pay less for electricity because I've eliminated the 50 or 60 hertz losses. And that's the reason to go to a C high pass type filter. Typically, you don't ever see above a frequency of the fifth harmonic. Okay, that's in my experience, the fifth harmonic is where we stop with the C high pass filter. Okay, it's a seven. It tends to be difficult even to find components to properly do it. So you might say, well, what's the difference between these two types of filters? On the left, I have a system that consists of notch filters. On the right, I have a system that consists of high pass filters. And again, these could be C high pass filters. It would be exactly the same result. And what you see is an impedance characteristic that looks like this. And you can see what we've done is we've eliminated these resonant points with high pass filters. We reduce or dampen that resonance down to these values here in red. But another thing that's interesting to note is at the tuning points, we lose our filtering with a high pass filter. So you give up your high impedance point between your tuning points, but at the same time, you're giving up your filtering at points here, and here. So this is where the art comes into play. How much dampening do I need, and how much filtering can I forego at the tuning points? This is the art of doing a harmonic analysis. Is you have to sometimes do an iterative process. You try to avoid notch high pass filters when you can because there's cost associated with it. If I have a harmonic current at this location, this would be true for a cycle converter, potentially true for a steel mill, where I have what's called interharmonics or non-integer harmonics. Then I need to be concerned about this resonant peak. It would be a harmonic current injection times this value of ohms to give you sometimes a very high voltage distortion. So the purpose of the high pass versus the notch filters. Oftentimes you see high pass filters being used to dampen resonance associated with capacitance. And sometimes you see high pass filters applied in parallel with capacitor banks to dampen resonance. It's a technique that's often used. This is the tuning point calculation. This is the tuning calculation. This is how we come up with the values of XL, XC, values of L, and values of C. I won't get into the equations too much, but this is the simplicity of it. The spreadsheet tool we have basically powers these equations. What's key here is that what we do is we come up with a value of X of Q effective. What is the megawatt output of the filter? How much reactive power do you want? Remember, that's the first rating for a harmonic filter. And from there, we come up with a value of Q effective. We can come up with a value X effective based upon Q effective. And really that represents the combined impedance of these two at 50 Hertz. And from there, we can then calculate X of C and X of L based upon a tuning point. So in this situation, you're coming up with those values. You come up with your value of X of C, which then allows you to calculate the rated kVAR or the capacitor. But again, now we need to pick, well, what voltage are we going to come up with? What capacitor voltage are we going to pick? Well, you have to calculate, well, what is the voltage here, right? We have harmonic current coming down. Harmonic current times this impedance creates voltage at each of the harmonic frequencies. Plus we have the 50 Hertz value of current at of voltage at the fundamental. They must all be added together to come up with a peak voltage rating of the capacitor. And then from there, we can then come up with a capacitor kVAR rating based on a capacitor voltage rating. Fundamentally, that's what we're talking about doing. And we're going to talk about that in a moment. So for a high pass filter, the beginning calculations is exactly the same. The key difference is when we come up with a damping factor, how we handle damping factor. And but the tuning calculation is exactly the same. The value coming up with X of C is exactly the same, and more or less coming up with the ratings for X of L is exactly the same. What changes here is the damping factor that we come up with. And C high pass filter, similar calculations, a bit more complex. Again, we don't go through these calculations when we do our analysis. We go to a spreadsheet tool, and it's how we do it. Most consulting firms are using some type of tool once the program comes up with this tuning point, and that's what I show here. It's fast. I can do a harmonic filter design in about 2 minutes. Okay, so the first thing you have to do is become confident that your calculations are right, that your spreadsheet tools are correct, that you understand what the spreadsheet tool does. Once you have that tool developed, you're designing filters very, very quickly. I use this spreadsheet tool in conjunction with a harmonic analysis program to go back and forth and come up with the parameters, inject that into Dixieland, and then we come up with the performance of the system. From a component selection and rating standpoint, you know, I show this over here because I can't overemphasize. You want to always be very conservative with the design, and it's really a cost of pennies on a dollar. You're already buying reactors, you're already buying capacitors, you're already buying resistors. It does not cost much more to say, well, I want a higher voltage rated capacitor. I want a more current rating in my iron core reactor. I want more higher watt rating in my resistors. And you do that, and it costs you maybe 10, 20, 30%. But what it does is it creates a very reliable system. One that and it goes back to the question that we had earlier, if somebody parks a harmonic filter next to your system and it does draw more harmonic current, that you have some small resonance that exists between those filters, that your filters can still be used, that it doesn't fail. So systems, why be conservative? Systems change. They change, systems expand. Without a doubt, some point down the road, they will want to expand and put more reactive compensation, more nonlinear load on the system. Calculations don't always match. Okay, I've been doing harmonic analysis for many years, and the reality is calculations don't always match the reality. They don't always match what happens in the system. So you got to make an assumption that I might have more harmonic current than I calculated. So having a conservative rating system in place is good, and you're not paying much for it. And this last one's very important. make sure you understand the suppliers you are working with. Iron core reactors are a specialty item. There is not a whole lot of reactor manufacturers worldwide that can build iron core reactors. So I will tell you that you want to vet the suppliers of the capacitors, the reactors, and the resistors. You should be using those key suppliers and not buying on price. If you buy on price, you will potentially be paying later because your filter system might not perform or it might fail prematurely. So we're going to talk about the three components: the capacitors, the reactors, and the resistors. And first of all, the standards. And I apologize, there's probably an Australian standard that belongs here, but the standards that I'm used to designing to more often than not are the IEC standards, Canadian standards, and the IEEE standards. To some degree, many of these standards are being homogenized nowadays. So I would say that even the Australian standards are very similar to these standards, if not the same. There's also some application standards other than just the component standards, and they're noted here. So these are good reference tools to go to when coming up with the choice of capacitors. From our standpoint, we're using these key suppliers, right? And there's not a whole lot of other ones that we're using. The capacitors can be internally fused or externally fused. And internally fused capacitors mean the capacitors are equipped with internal fuses, usually many small fuses. It's really a geographical based system. I believe Australia is more involved in using internally fused capacitors, where in North America we are almost always externally fused capacitors. I can argue why externally fused capacitors are better than internally fused capacitors, and I'm telling you, you can find somebody out there who will argue equally as strong about internally fused capacitors being better than externally fused capacitors. So I say stick with what's normal in your territory. If internally fused capacitors are being used in Australia, then continue to use those because it's the typical one's about equal to the other. So when you're doing your design, when you're choosing your capacitor, you're more or less taking your filter current at each of the frequencies multiplying times X of C. Remember, X of C drops with frequency, right? X of C drops with frequency. So as you go up to the second harmonic, the X of C is 1/2 its value. When you go up to the fifth, it's 1/5 its value at the fundamental. So you're calculating the voltage at various locations. You're calculating the peak voltage, and you're also calculating the RMS voltage using these formulas here. And the standards dictate these values that are allowable for a given capacitor. So this is the way we make choices. Basically, in our spreadsheet tool, we actually use a flagging mechanism. We will not exceed these values, okay, in the design for the maximum current. And again, the maximum current being a very conservative current that we have chosen for the design. That's the philosophy that should be followed. We kind of have a starting point here, 1.25 times the fundamental is a good starting point. So if I have my normal line to neutral voltage here, I would typically at least start at a value of about 1.25 times that value to come up with my value of X of C. It's a starting point. It's not always going to be correct. Depends on how much current you have flowing into your filter. Capacitor manufacturers oftentimes have what's called standard duty, heavy duty, extreme duty. Do know that these values change from one supplier to the next. So you have to look at these values, what is that value? What is, right? We have different values. I can tell you that a standard duty capacitor or heavy duty capacitor, I think more so than standard heavy duty capacitor from ABB is different than a heavy duty capacitor from General Electric or Eaton. They're just different. So understand the capacitor that you're picking, make sure that you're applying it within its rating. So One of the things that's interesting to note is that when you go to the capacitor supplier, you do not need to pick one of the standard capacitors. You can pick, here we're showing standard ratings of 300, 400, 500, 600. If you're doing filter design and you come up with a value of 575 kVAR at some funny voltage, well, give that to the supplier, the capacitor bank supply, the capacitor supplier, and tell them that's what you want. They'll come back and give you that design, and you're not paying a premium for it. It's a kind of something that you realize after a while is just pick the values you want. We do make a recommendation though in a multi-tune capacitor bank that you design the filter so that it uses the same capacitors throughout. And that's a recommendation, is to come up with designs that utilize the same voltage rating, same kVAR rated capacitors throughout, because it decreases the number of spare components required on site. Internally fused capacitors is interesting to note. Typically, we're dealing with voltages that stop at about 12 kV for the capacitor, which means that for higher voltage systems, typically those voltages up at the 23 kV level, we're going to be putting two capacitors in series to achieve their necessary voltage rating. So that's a key advantage, by the way, of the single bushing of a externally fused capacitor, is that I can get to about 24 kV with an externally fused capacitor. Internally fused capacitor, I must use two in series. So remember that just pick the kVAR and voltage rating you need, give that to the capacitor bank supplier, and they'll make it happen for you. And you're not paying much for that custom size capacitor. They all come with discharge resistors. Typically, it's a 5-minute discharge. They'll take the capacitor from peak voltage and drop it down to 50 volts or less in 5 minutes, 300 seconds. So that's pretty much standard. This is an internal shot of an externally fused capacitor. Here's that resistor here. So this is some typical capacitor weights to consider. Again, these are externally fused capacitors that we're showing here, but these are typical weights. Unfortunately, I'm in pounds. Apologize for that, so you have to do the conversion of kilograms. But you can see that 100 pounds is a fairly heavy capacitor. 150 pounds, a fairly heavy capacitor. Internally fused capacitors can get to be much heavier. This is from ABB Capacitor Group in Quebec City. I show this slide because it's interesting to note the failure rate for capacitors is very low, very, very low, on the order of about 1 in 5,000. Okay, so capacitor technology has advanced in the past 15 years, last 20 years, when they have gone from polypropylene paper design towards polypropylene designs. The number of leaks that they get, the number of capacitor failures they get has gone down quite a bit. But key here is still to remember is that increasing the voltage rating of the capacitor inside the harmonic filter will help to create a more reliable harmonic filter, because you're going to be stressing it less, and you're going to be paying pennies on a dollar to increase that. Blown fuse detection, just realize that whenever there's a capacitor bank within a harmonic filter bank, we're doing some type of blown fuse detection. Either it's going to be a split Y, where we put a CT in the neutral of two Y-connected capacitor banks to detect a harmonic current, current flow through here because of an impedance imbalance in your filter, because we've had a fuse operate. And that could be an internal fuse or an external fuse. And then again, we can use voltage for voltage. This is NEPSI's preferred reason. We can't get into reasons why, but there are reasons why the split Y with a CT in the neutral is a better choice for blown fuse detection. Incidentally, for externally fused capacitors, we also use a micro switch assembly here, and we detect a fuse operation here with the operation of a micro switch inside or connected to that fuse. So The formulas are simple. Again, we have a spreadsheet tool on our website for making the calculations for that neutral and balance scheme. For the iron core reactors, or air core reactors, here I'm showing the iron core reactors, the standards that apply, and again, IEC, IEEE standards are shown here. There's really not a standard that applies to harmonic filter reactors. These are the ones that are closest to the standards that are utilized in harmonic filters. What we're showing here is a single phase iron core reactor. A key characteristic of iron core reactors is that the magnetic flux stays inside the core of the reactor. Okay, that has some advantages, and it is why we use them in the metal closed harmonic filter banks, is that we can't have an external magnetic field. So somebody was asking a question about the voltage and current induced on the fence of a substation that might have a harmonic filter. It will be because air core reactors are being used, and we're going to talk about this in a second. Air core reactors are being used. These are North American suppliers. I'm not sure if they're located also in Australia, but I'm sure you have suppliers local there also. So we've got some kind of characteristics here I'm showing. Normally we're talking single phase reactors, or sometimes three-phase reactors. These iron core reactors can get quite heavy. They're using an iron core gap design in a floating core design. Floating core because I have insulators here. And if you remember during maybe I'll show in a minute, but the impedance of the reactor is small relative to the capacitor of the fundamental voltage. So the majority of the voltage drop in a harmonic filter is across the capacitor and not across the reactor. And therefore, putting the reactor up on insulators will help to improve the reliability of the design, because typically we might only have 500 volts across the reactor coil when operated at 50 or 60 hertz, that voltage. So it's very low voltage. The design of the filter is still, of that reactor is still designed for medium voltage, but yet the normal voltage stress during normal operation is very low. It's only during the switching operation that you get a voltage stress. So we show an iron core reactor on the left. Remember, associate iron core reactors with a metal closed filter or an EHAUS solution. On the right is an open air filter component. The air core reactor is what you're going to get when you're doing an open air design. In a sense, these designs are very similar. The only difference is air is being used here to create inductance, where here iron is being used to create inductance. The iron core supports the reactor winding here, and here you have aluminum webbing here that supports the winding. The incoming winding is tacked to the webbing, and it's raised up in voltage. So you could call this a floating core or floating air core reactor. We have insulators on the bottom. Same concept is used here on the iron core reactor. It's the iron that helps to produce, to reduce the size and to encapsulate the magnetic field associated with the reactor. So from an external view, the air core reactor has a very large magnetic field. If I have a fence over here, it's going to get magnetic heating. And you're going to get induced currents in it, and you're going to get heating. So air core reactors and the open air filter design requires a lot more space. It's one of the reasons why some companies go with metal closed harmonic filters. It's much more compact, typically about 20% of the footprint area. So I've shown the difference between iron core and air core reactors here. Again, the advantage of iron core, no stray losses. But a key advantage of air core reactors, they're not susceptible to saturation. You don't get saturation in an air core reactor. Saturation in an iron core reactor can result in failure. And it is why I say that you want to make sure that your filter current specifications are high. You want to specify the harmonic current that the reactor is going to be asked to filter or to conduct. is much higher than what maybe you had estimated in your analysis. So a conservative reactor specification, especially when it's iron core, is highly advisable. So depending upon the tuning points, the iron core reactors can be less expensive. As you go up in megabars, the value of inductance goes down, and oftentimes air core reactors can become more competitive in price. So here's an example of an iron core reactor. This is me standing there. So that's a very large harmonic filter reactor. We got some temperature ratings over here that we're talking about. Because of timing, I can't get into it too much, but do realize that our recommendation is to speak with your iron core reactor or air core reactor supplier and let them pick the temperature rise that you need for the project. These the reactor suppliers are specialized in harmonic filter design. Reactors that go into harmonic filters know the installation system they're using. I recommend that you go with them. The key here, though, is what ambient temperature you pick. Make sure you pick the correct ambient temperature. For us, we always pick at least 60 C ambient inside the enclosure. Even if it's a 40 C ambient, we'll pick a 60 C ambient temperature inside the enclosure. Why? Because inside the enclosure is hotter than outside the enclosure. So it's important that that you properly specify the ambient temperature, because the reactor design will be impacted by that ambient temperature. And be conservative with your harmonic current ratings again, because if you pick wrong and the reactors are saturating because you picked wrong, or an air core reactor because it's overheating because you didn't put enough current rating in the reactor, you will have a filter system that can't operate. So this is a picture of iron core reactor single phase. I don't have time to get into it in too much detail, and do realize that for smaller systems, oftentimes 3-phase iron core reactors are being used. This is typically at the 15 kV level. We might get up to about 3 megabar filter tuned to the 5th harmonic would be a typical size, 3 megabars. Oftentimes also the BIL, we're going up to maximum 95 kV BIL. Key difference between single phase and 3-phase reactors is the core is grounded in a 3-phase reactor design, and the voltage stress now that exists between the winding and the core is the line, basically the line to neutral voltage of the system. So you have a continuous high voltage condition across the installation system. In my opinion, the 3-phase reactor is a less reliable design. So voltage stress is in a typical iron core design. Again, you can go back to watch the video, see what this is all about, but we're able to distribute the voltage in the system and improve the reliability of the harmonic filter by using a floating core design. And we show the same thing at 34.5 kV, so 2 different voltage levels. This is a stacked core design, a very good reactor manufacturer, and what you see here is all the gaps that are being used, and it's just a significant number of gaps being used. This is how the inductance is created in a iron core reactor, and it's also very complex, and that's why there's only a few suppliers out there that can properly do it. Our spreadsheet tool will provide the necessary data for a reactor supplier to quote a reactor. So on a website, that tool that is used to produce the harmonic filter design, the selection of the components will also come up with the correct component ratings for the inductor. So remember, we're pushing current. Harmonic analysis comes up with a value of current at each and every harmonic that's going to be flowing through that reactor. That reactor must be rated to carry all those components. What we give the reactor supplier is what you see here to the right. It's exactly what we give. And you can see here some design margins. We at least have these types of design margins. I can't overstress this one here. This is our philosophy: multiply the fundamental by 1.5. Do we always do that? No. But if it's a harmonic filter and we're looking and it's going into a process industry where we're looking for high reliability, we're multiplying the fundamental current by 1.5, despite the fact that you will only have a 10% over voltage in the system, and it will result in that 1.5 per unit. But if you knew what the reactor suppliers were doing, they're building a custom wound device. It's not something that is used over and over again. They don't know the cooling capacity within the enclosure system that you're supplying, and therefore it can be that their design and analysis tools that they use to develop the iron core reactor might be not conservative enough. So by putting this in there, it's helping to guarantee that the filter reactor that you have is correct. It's also helping to guarantee that you will not ever enter into a saturation condition, trying to avoid saturation. So we go with a 1.5 multiplier on the current, and then we decide from there to rate and the protective devices. So if we take our harmonic currents, we multiply by 1.5, it means we can set our protection devices at 1.0 per unit current. So that is kind of our philosophy. Just some different designs here: air core reactors, stacked arrangement. We show it here. Again, this is R, and this is the X of L and the C. So we have a three-phase stacked reactor arrangement, air core. And then here we have the same type of reactors, but on the ground, at ground level. And they're large, probably a low tuning point here is what's going on. And therefore, they're on the ground. So they're not as good in seismic conditions, incidentally. Something like this does not have good seismic capability. So if you go into a high seismic zone, not in a very good locations for that. When you do look at air core reactors, this goes back to the situation of eddy current heating in the fence, as step voltage in the fencing around a filter design. When you do look at air core reactors, they do have a magnetic field clearance requirements, often quoted, MC1, MC2. These are multiples of the coil diameter as we show here. And these are just typical numbers, but what it does is it increases the footprint of the design, because I cannot put a fence inside this area here. I cannot put a fence inside the area or other large metallic parts forming closed loops. So incidentally, air core reactors typically take up more space because of the external magnetic fields. And that magnetic field requirements are also in the axial direction, also, in other words, above the reactor and also below the reactor. In this design here, if you're not careful, you have a significant amount of magnetic field entering and penetrating the ground. If we have ground grid here, it can cause heating. So you have to take into account things like the fence here, the rebar or the copper ground grid underneath. If you have rebar in a concrete, all these things can result in heating because of the magnetic field associated with their core reactor. So you have to make sure that you pay attention to your design and consider the eddy currents within the on the external side of the air core reactors. So resistors, again, we're putting them on top. Look for low inductance. We prefer stainless steel stamped grid design. We typically see ratings no more than, say, 200 kW, and we're closer, I think, to 150, 180, 200 kW per phase. You think about it, there's a lot of losses in a resistor. The resistors go inside an enclosure like this. It's well ventilated. We prefer to not use any type of convective cooling. I mean, no forced cooling. We prefer not to use any forced cooling in the design. So the calculations for calculating the losses it basically essentially is to determine the voltage across the resistor through calculations, and then to take V squared over R, come up with the watts per phase. And again, here you want to be conservative. Why? Because you may have more harmonic current flow than what you anticipate. So be conservative. The other reason to be conservative, I will show you in a minute, is that it allows you some flexibility in dampening factor in your filter design. So C-high pass filter, the formulas just get a bit more complicated, but again, they're there, and they're all in that spreadsheet tool. The stamp grid design is shown here. If you go with a higher watt rating than you need, one of the other advantages is that I can tap off of these points here and come up with lower values of R, or if you ship it at some lower value here, we can then increase the resistance. So it's what we would call designing flexibility into a harmonic filter. It allows you to tap the resistor if you can put more rating into the resistor. So putting more rating in the resistor gives you a backup plan. Say I need to increase my dampening of the filter. Well, by putting a larger resistor in there, I can then tap my resistor down to a lower resistance value and improve the dampening factor. And so vice versa, by the way, it works in the opposite direction. These are what you need to specify, but generally speaking, BIL is important. What is the system voltage is another important. Consider elevation effects. If I'm higher than, say, 1,000 meters, you want to make sure that you're considering the effects of elevation from a cooling standpoint, but also from a insulation, voltage insulation standpoint. Specify stainless steel grid resistors when at all possible, because they're just more resilient. These are what I would say bulletproof design. There's not much things that can fail that design, especially if you put some rating factor in there. There's also this rating factor thing. These typically have a 5 kV rating to it. So we typically take our line to neutral voltage and divide by 5 kV, and we would put the number of these in series. So a 33 kV system is roughly, I don't know the numbers, let's do 34.5. That's what I'm typically used to. That's equal to 19.9 kV line to neutral. We would take that 19.9 kV divided by 5 and basically put 4 of these in series. And the reason being is during switching operations, you can get a voltage strike through the resistor because of the transient voltage. So we are about done. I'm going to go through questions. Remember that we talked about L, R, and C. There's also voltage. There's also the control and protection system, which can get also quite complicated. All harmonic filters have a control and protection system. Open air solutions typically is a separate device, oftentimes supplied by a different vendor. Metal closed solution is always part of the equipment. Of course, it's got advantages. Why? Because we're supplying that control and protection system. When you look at it, it consists of many different types of relays. Remember that most overcurrent relays do not sense harmonic current. They are filtering out the harmonic current, and they're responding to fundamental values. And therefore, to protect harmonic filters, it's typically best to use some type of metering device. We use a Schweitzer 735, but there are other devices. But power quality meters with relay outputs can better protect a harmonic filter than an overcurrent relay can, because overcurrent relays are looking at fundamental. We like to look at all the values, RMS, THD, and various harmonic currents. So there is a complex part of the design of harmonic filters, and that is control and protection. This is just a snapshot of a typical 3-stage system and all the protection and control that we would typically provide. Actually, this is a protection diagram only. So we have, these are ANSI device numbers, but we define what they mean over here to the right. So again, go back to the video if you're interested in this. Another thing to note is we want to make sure we have no out of sequence control of the bank. Generally speaking, multi-tune filter banks must step up and step down in sequence. So that's part of the control scheme. So just kind of another picture. And we have other presentations we could potentially do in the future if there's interest in that, and that is designing flexibility into filters, how we design flexibility into filters and come up with various characteristics of a filter that I would say give you a backup plan should you need one. So, that's the presentation. Let me go through some questions real quick. I'm going to scroll up.
Yeah.
If you guys do have questions, please do ask.
Did you want me to run through some of those with you, Paul? Thank you very much for that, mate. It was very, very interesting. And obviously, I mean, you've had to glean over a lot of stuff. Obviously, many, as you said, in your introduction and in talking through the many, many years of experience and learnings in there. Do you want me to pose the questions to you and you respond, or are you happy to read them off for the ones?
It's up to you, whichever way you prefer.
All right, I've got a track of them, and I've tried to round out the ones that I think you've already covered off. So the first one that I've got that I believe is still open is, so what if the grid, so this is from Stain, what if the grid reactive power requirements are inductive at the fundamental frequency, for example, for offshore wind power plants?
That's a good question. So this is a situation where the grid code requirement is that the system be inductive. Harmonic filters, by their nature, are capacitive, and which means that you have to put in a shunt reactor. It's put in a shunt reactor to compensate for the harmonic filtering. We just had a project we did, I don't know, about a year ago, where the system it needed 5 megavar shunt reactor to compensate for a 5 megavar C-high pass filter that was part of the system for the light load condition. So remember, the harmonic filter the shunt reactors will not interfere with the impedance network from a resonance standpoint. But if you need to do filtering, then of course you need to put some shunt inductive reactance in addition to the filter bank capacitive reactance. And one of the things to remember about filter design is that if you go with a very small kVAR, a lot of times it becomes much more critical that you get the filter design exactly right. You know, you could say you had a harmonic filter, let's say you have a 30 megawatt system, 100 megawatt system. If I put a 100 kVAR filter in, you could tune it exactly in your program and probably get it to behave, look right. But the reality is it's just a sliver of a filter in the impedance scan, and it's not going to perform out in the field because of various things in the filter. So we find that you have to have some reasonable size filter system, 5 megavars, 10 megavars, you know, for a very large, you know, power plant situation. Otherwise, you can't design that filter to do its job correctly. So it becomes difficult because you're adding cost to the system. You're adding shunt reactance, shunt inductive reactance at the same time that you're adding capacitance to the network to develop your filter system. So I'm ready for the next question.
All right. Yeah, thanks very much for that. I think you covered it off there. I guess we'll jump a little bit around in the questions because there was another one along a similar line. And I should mention, if people do have to drop off, we'll keep trying to work through the questions for a few more minutes, but Paul's details will be available at the end of this presentation. We'll put them up. They'll also be in the recording, obviously. You are able to contact Paul if you have any follow-up questions. But I've got one here from Jason along the same line, talking about wind and solar, so the renewable generation field. And the question is harmonic mitigation commonly required for wind and solar farms in North or South America? Where do you see the role of active filtering in this area?
My experience is that in South America so far, and also in North America, minus Quebec, which is the eastern province of Canada, one of the eastern provinces of Canada, is that capacitor banks are most often being utilized. That the developers are staying as far away from filters because of cost as they can. In Quebec, the interconnecting utility defines a impedance loci, and as a result of the way they define the impedance loci, oftentimes those wind farm developers are pushed into developing a harmonic filter for their projects. So in that area, we're seeing more harmonic filters, but in just about every other area that we're shipping into right now, we're seeing capacitor banks. This is North America, and also in South America, we just see standard capacitor banks. We employ a concept called filter-ready capacitor banks, and what that means is that we design a filter bank, a capacitor bank that can be easily converted to a harmonic filter. So we call it the backup plan. And the reality is, when you do harmonic studies, oftentimes it's inconclusive, especially if you're applying IEEE 519. It's inconclusive if you will exceed the limits. It depends upon how do you sum up your harmonic currents associated with each inverter or each turbine, and also how sharp the resonance is. I got a whole presentation on this matter. Will determine if you pass or fail at your harmonic standards. So from our standpoint, filter ready concept provides a backup plan to the supplier. I think from an active filtering standpoint, we haven't seen where it's cost effective at this point. And you cannot use an active filter system where a system is using capacitors, and that's because capacitors will come in and out of resonance, and the active filter will be able to control the harmonic current flow in the system. So you're still going to be pushed into what's called a detuned capacitor bank, which is another way of saying a harmonic filter tuned to the 4.0 or 4.2, which means you've already carried a significant cost to be able to employ a active filtering. So we have not seen active filtering as a viable solution at the moment from our perspective.
Yeah, okay, that's really interesting, and definitely in that cost sensitivity. So another one, quite an interesting one. So Darren has asked, in situations where network operators or network owners do not have power system models of their network, what options might be available to design a filter to address emissions from inverter-based technologies? So again, along that renewables application. Do you have any recommendations around that lack of network model or lack of?
Yeah. So the first thing to consider is what is the harmonic current injection. Being inverters is going to be very low. My recommendation would be to go with a filter similar to what you see here, either high pass filter or a C high pass filter, and you create an impedance profile that's very damped. So just a single tuned filter that's damped, meaning it's not going to excite or magnify harmonic currents because it created a very flat impedance curve. C high pass filters and high pass filters, but especially C high pass filters that are heavily damped, are, I call them, almost a no-brain solution. You're paying a little bit more for it, but you're not going to magnify currents at a frequency that you don't intend to, but yet you'll still get some filtering capability. So I would say lean towards a high pass or C high pass filter, and that would be for renewables. If you're dealing with industrial facility, knowing the harmonic current, the total harmonic current of the system that's available for the filter, it would be the starting point, and then to design filters that would be able to absorb 100% of that current would be a conservative way of approaching it.
Yeah, thank you. I guess one that has flowed on to the end of that I think you've alluded to a little bit there, but Yatin was asking initially about what does conservative mean, and you've covered in your presentation some of the recommendations, but the question then flowed on to does being conservative also apply to harmonic frequencies and the number of harmonic frequencies, and how you tune that, or is it purely in rating a plan?
So from our standpoint, when we are conservative, we are typically choosing current flow into the filter at each and every frequency to be significantly more than what is predicted by an analysis. And then we're also looking at the fundamental. We're multiplying that times 1.5 for the reactor design alone, not for the capacitor, only for the reactor. What's key here is that I often employ a concept called, is it a 100% rated reactor? Is it a 50% rated reactor? And in this case, my fifth harmonic current, you can kind of see here, is almost equal to the fundamental. So I would call that a 100% rated reactor. And that would be what I would consider a conservative design. But that's not always conservative in the sense, because I might have a system where I have 300 amps of fifth harmonic current. And if that was the case, I would say it's not a conservative design. I would say you should go to something at least 1.5 times that, if not more. So we design the harmonic currents and the tuning points in a way that, and I'll give you an example. I think it's the best way to do it. If I were to do an analysis and I determined that my fifth harmonic current is going to flow into the filter is say 50 amps, I would at that point say that the fundamental current of the system of that filter branch should be 100. I would double it, say it should be 100. I would take 100 times the line-to-line voltage times the square root of 3. That would become my reactive power rating of that filter stage. But then I would rate the harmonic current at 100%. In other words, the fifth harmonic equal to the fundamental. That would then become a relatively conservative design, because it would allow my harmonic current to grow by another 50 amps, by another 50%. So that's just the way we would typically approach a conservative design if we know the values of current.
Yeah, thank you very much. I think, yeah, like you said, that's emphasized a number of times. It's easiest to allow for that up front. It's very hard to come back in future and tweak it once it's on site and installed.
Yeah, well, think about this. We built an enclosure around that reactor, and now you determine that the reactor needs to be bigger. Well, there's no space for it, right? So
redesigning a whole plant.
You could potentially be doing it, and then you have the cost to pull this out of an enclosure. If it's an air core reactor, you're going into it. So even this one here, if the reactor got to be bigger, it would start to interfere with the adjacent components. So you now have field work versus factory work, and it's very expensive. And you have, of course, the downtime of the facility that we did your miscalculation at.
Thank you. Do you have a few more to go? We'll try and get through them, but if there's some really good answers and responses come through, thank you, Paul. So if we start to run a little bit short on time, we'll have to prioritise a few. But Joanne had one. So you spoke a lot around the harmonic filtering for lower harmonics. I think you're talking around 4.7 and 5 for some of the examples. Joanne's question talks to, is it recommended to use harmonic filters for harmonic violations greater than the 30th harmonic?
Yeah, that's a good question. When you do harmonic filter design, the general concept is to start at low tuning frequencies and work your way up. The reason being is that you get this resonant point that sits below the tuning frequency. So if you have a single harmonic of concern, and it says greater than the 30th harmonic, you can put in just a single, say, 30th tuned harmonic filter. The issue is you get the resonant point that exists below the tuning point that you need to deal with. So the solution to that is to put in a damped harmonic filter, or a C high pass or high pass filter. It's going to be a high pass filter because of frequency, and you can take care of that violation. But that's how you deal with it with a high pass filter.
Fantastic, thank you. This one might be a relatively quick one. There's one from Kenny talking about the tool that you've developed and that's available on your website. And Kenny has said, is it the tool neutral to IEEE and IEC compliant?
Yes, I think the answer to that is 98%. It works. It works for both. The tool has a selection of what capacitor ratings are you at? Are you looking at 20%, or 25%, or 35% over voltage rating on the capacitor? Remember, we came up with this concept of XD and HD design, the standard duty design. So you can select the design capacitor in its over voltage parameters. But in either case, we're calculating the peak voltage, the RMS voltage, the kVAR, and the RMS current for the capacitors. For the reactors, it really doesn't apply. It's really the capacitors that, when you talk IEEE or IEC standards, that you're concerned about. And I think you could get your numbers that you need from there. They actually may still be the same.
Yeah, okay. So that does sound like something even to reach out to you if there's any further questions about that tool.
Yeah, and I might actually, it's a good question. I may modify the tool actually to accommodate the IEC standards. I'll just have to look at what the standard ratings are for the IEC guys to see how much different they are compared to the IEEE, to see if there's enough of a reason to do that.
So we've got a couple more that we should be able to get through if you're able to spare a few extra minutes, Paul. I know we're over time. And so we've got one from Hussein that says, what are your suggested commissioning tests for harmonic filters?
So our recommendations, generally speaking, is we first of all, from once you get a harmonic filter design, we do recommend at the factory that testing does get done. All harmonic filters are custom in nature, and therefore they should be treated as if you're going to type test the equipment. So we recommend in-post testing, high pot testing, and SFR8 testing, which is frequency resonance analysis, to come up with an impedance profile similar to this, to confirm that your filter impedance profile matches that of the study, and then partial discharge testing to confirm that the system is going to last 20 years. If you have partial discharge, it means you have corona. So that's the key assembly type things that we recommend. For the harmonic filter reactors, if it's a critical application, you may want to consider doing a heat run on the reactors, at least on one, and also a linearity test up to 250% on the iron core reactors. So these are factory tests that we highly recommend. It helps to guarantee that the system you bought is going to be correct. Once it gets in the field, all the testing that you would typically do for high voltage electrical equipment should be done. This includes high pots in the field. We would recommend consideration be given to SFR8 testing, a repeat of the test. If it's air core design, it's being assembled on site, so an SFR8 test on site should be certainly done. A functional test of all the protection and control system, relay calibration. And then once it's started up and running, we need to do some validation at that point. Is the reactor power right? Is my performance matching that of the study? And you're doing that. If you've specified the equipment to contain power quality meters, these types of tests become quite simple to accomplish in the field.
Thank you very much for that. So obviously many different tests to be doing. I'm sure that's covering just the early stages or the key ones as well. We do have two more from Carl, but Carl, apologies, I might just pick the first one you asked because we are a bit over time. So Carl's questions was, does the quality factor have an effect on the performance of a C-type high-pass filter?
Yes, yeah. So we'll answer that real quick with this figure here. This one here. Perhaps you can see it, but obviously as you change the damping factor I'm changing the damping factor of 3 filters here. You can see the impedance characteristics of the filter significantly changes. So yes, it has a big difference. In this case, the first filter branch is a C-high pass. But remember, C-high pass, whether it's C-high pass or high pass, the damping factor is going to have an effect on it. Again, remember, C-high pass filters fit tuning point and below is where you typically see it. I think that actually answers your next question. Carl had a question. C-high pass type tends to increase a little order harmonics close to the tuning point. Yeah, so when you do, remember when you do high pass filtering, you lose your filtering capability at the tuning point, and you're trading that off for how much damping you're getting with at your anti-resonant point in your filter.
Thank you very much. Did well, able to nail both answers or both questions with one answer. Well, thank you, Paul, for your time. Obviously, extremely in-depth presentation with the potential, as you said, to go on to another level talking about the dynamics. So hopefully we'll look forward to hearing that one in the future, but do really appreciate your time. To close out the session, if there were any questions that we've missed there or any questions that have come up, Paul's details are on the screen now. I will leave them up for a short period after the end of this presentation. Please do get in touch with Paul if you do have any follow-up questions. I guess being mindful, Paul, I imagine you're quite busy and may need some time to respond.
Okay.
Also, from the Seagray NGN side, if you want to get in contact with Seagray NGN, I've got the events website down there below. I'd recommend jumping on, having a look at that, or dropping an email. But thank you, Paul. Really appreciate it. A very expansive field, really, when you start to pull the covers back on it.
Yes. Okay. Great. All right, guys. Thank you. Thank you for everybody attending also. Appreciate you guys coming on.
Thanks very much for your time.
Yep. We'll see you.